Welcome to The Explainer. Today we're diving into a detective story. But this isn't your typical whodunit. No, our crime scene is the world of mathematics. And our suspect? It's just a number. But this one number, well, it broke all the rules and threatened to tear down an entire way of thinking.
So let me ask you something. What if a number could actually break all the rules? I mean, think about it. Imagine a world where everything is neat, tidy, totally predictable. And then bam, one number shows up that just doesn't belong. A number so weird, so out of place, it had to be kept secret. That's the mystery we're getting into today. So to really get this, we have to set the scene. We're heading way back to ancient Greece. And from them, you have to understand the world of numbers was, well, it was perfect. Everything had its place. See, the ancient Greeks believed that all numbers were rational. That just means you could write any number as a simple fraction, like 2/3 or 8/12. This wasn't just math for them, it was their whole philosophy. They thought everything, the planets, music, you name it, could be explained by these nice, simple ratios. A totally logical and orderly universe. But then, a new number shows up. A mysterious character enters the scene, the square root of 2. And it came from something super simple, just the diagonal of a basic square. It looked harmless enough, but it just wouldn't play by the rules. It didn't seem to fit into any of their neat little fractions. And this is where our case really begins. Okay, so how do we prove a number is, well, a rule breaker? We're going to use this incredible detective tool from the world of logic. It's called proof by contradiction. And trust me, it's brilliant. Here's how it works, and it's actually pretty simple. To prove something is true, you start by pretending it's false. You assume the exact opposite. Then you just follow the logic, step by step, and see where it takes you. If your assumption leads you to something totally impossible, a complete paradox, then you know your original assumption had to be wrong. So let's do it. Step 1. We're going to assume the square root of 2 is not a rule breaker. We'll pretend it's a perfectly normal, rational number. We're going to say, okay, square root of 2, you can be written as a fraction. Now, let's follow that trail of logic and see what we find. Okay, but before we start, there is one crucial condition, a ground rule for our investigation. If we're going to write the square root of 2 as a fraction, let's call it m over n, we have to agree that this fraction is in its simplest possible form, right? I mean, you'd write 2/3, not 4/6. So m and n can't have any common factors. This is super important. In fact, it's the key to the whole thing. All right, ground rules are set, assumption is made. Let's start following this logical trail and see where it goes. Okay, so we start with our equation. The square root of 2 equals m over n. Pretty simple. Let's get rid of that pesky square root by squaring both sides. Now we have 2 equals m squared over n squared. A little rearranging and we get 2 times n squared equals m squared. Now stop right there. Look at that. M squared is equal to 2 times something. And what do we know about any number multiplied by 2? It's gotta be even. So boom, our first clue. M squared is an even number. And this points to a really basic rule about numbers. If you multiply an odd number by an odd number, you always get an odd number. Like 3 times 3 is 9. But if you multiply an even by an even, you get an even. Like 4 times 4 is 16. So the only way for a number squared to be even is if the original number was even in the first place. So what does that mean for us? Well, if m squared is even, then m times itself has to be even. There's just no other way. And if m is an even number, we can describe it as 2 times some other number, right? Let's just call that other number a. So from here on out, we know that m is the same as 2a. Okay, now for the fun part. Let's take this new piece of information, that m equals 2a, and plug it back into our equation from before. So instead of m squared, we have 2a squared. That simplifies to 4a squared. So now we have 2n squared equals 4a squared. Divide both sides by 2 and wait a minute, look at that. We get n squared equals 2a squared. We're right back where we started. This means that n squared is also an even number. That's our second major clue. And we just established the rule, right? If a number squared is even, the number itself has to be even. So that means n is also an even number. Now things are getting really interesting. Okay, everybody stop. Let's just pause for a second. We need to take a look at what just happened here. We started with one simple, innocent-looking assumption, and the logic has led us somewhere unexpected. This is the moment that blows the whole case wide open. So let's review the evidence. We followed all the clues, and what did we find? We proved that m, the number on top of our fraction, has to be even. And then we prove that n, the number on the bottom, also has to be even. Both of them. That's the undeniable conclusion of our logical investigation. And that, my friends, is the smoking gun. That's the contradiction. Remember the one rule we started with? The one non-negotiable condition? We said the fraction m over n had to be in its simplest form. But wait, if m is even and n is even, what does that mean? It means they both can be divided by 2. They share a common factor. So the fraction is not in its simplest form. Our logic has completely broken our own starting rule. We've created a paradox. It's impossible. Our starting assumption and our final conclusion can't both be true at the same time. And here's the thing. The logic we followed? It's perfect. The algebra is flawless. So if the steps are right, there's only one thing that could possibly be wrong. The place where we started. Our very first assumption. So the verdict is in. Our initial assumption that the square root of 2 could be written as a simple fraction was wrong. It just has to be. And if a number isn't rational, what is it? Well, there's only one other option. It must be irrational. An irrational number is just a number that you can't write as a simple fraction. The square root of 2 is guilty of being irrational. Case closed. You know, this discovery was a huge deal. It completely shattered the Greeks' idea of a perfect, orderly universe. The legend even says they tried to hide this discovery because it was so disturbing to them. It proved that the world of numbers was way more complex and mysterious than they ever thought. And it just makes you wonder, right? What other amazing, mind-bending truths are out there just hiding in plain sight, waiting for someone to follow the clues?